Okay. So now, last class we talked a little bit about some of the kinematics of simple harmonic motion. And I want to go back to something that we talked about near the end. Okay. We had this equation, acceleration as a function of time is equal to negative omega squared x of t. Now, we've mentioned the term differential equation before. Okay. This is definitely a differential equation. Okay. This is, okay, I've been trying to think which way you feel more comfortable with. Okay, acceleration is the second derivative of x. Okay, so this is x, second derivative with respect to time, is equal to negative omega squared x of t. Okay, now, there's a couple things that we have to go through on this. This is the fundamental equation of simple harmonic motion. First, we have the fact that the acceleration is proportional to the position. Okay? That's number one. A and x are opposite in sign. So, if A is at its maximum value, x is at its minimum value. When A is 0, x is 0. Okay, and if you think back to the mass going up and down in the demonstration the other day, when x was at its highest point, okay, the acceleration downward was going to be the most. When the mass was at the bottom, okay, which would mean that x is minimized, the acceleration, okay, was going to be most up because the spring is going to be the dominant force at that point. And when they're at equilibrium, okay, we said that x was 0, and we said that the acceleration was also equal to 0 there because the forces were in balance at equilibrium. All right, one final thing here, and this is a big one. This is right here. We say that A and x, the acceleration and position are proportional to each other. Okay? The constant of proportionality is omega squared. Constant of proportionality is omega squared. That's big. Because no matter what you see, and this is definitely something you can see in a multiple choice section, okay? You can definitely see something where you have some sort of weird function that's the second derivative of this function, okay? And then this would be the constant of proportionality. Okay? So no matter what happens in a simple harmonic motion, this term right here is going to be, that constant of proportionality is going to be omega squared. Okay, remember omega was 2 pi over the period. So now, one other thing, so you have to remember this. Another thing I want to take a look at is what's called the small angle approximation. So now, I'm going to make a column of theta in degrees, theta in radians, and sine of theta. Okay. It honestly doesn't matter which one I do, whether I take sine of theta, whatever, with because I'm going to get the same result. The only reason why I put the degrees in there is that you guys have a sense of, you have a better feel, more intuitive feel for the for degrees. So now, if I do 90 degrees, okay, theta in radians is pi over 2, which is 1.57. Now, the sine of pi over 2, or 90 degrees, is equal to 1. Say, okay, well, that's not very profound. It's true. Okay. 90 degrees really doesn't give us anything interesting there. So let's cut this down to 45 degrees. 45 degrees gives me 0.785. That's pi over 2 radian, pi over 4 radians, and this gives me 0.707. Again, nothing terribly interesting, but these are getting a little closer together. I have to switch colors because the black marker is definitely dying. All right, let's say go get 30 degrees. Well, at 30 degrees, that's going to be pi over 6, and that's 0.524. And this is sine of 30 degrees we know is 1/2, 0.500. Well, these two are pretty far apart. These two are getting a little closer. These a little closer again. Pretty darn close. Okay, now we're talking about an error. Here I'm not going to worry about the error for the first couple terms there. Don't worry about it. I don't care about these two. So now, right here, okay, from the true value of 500, I'm off by about 5%. Okay, yeah. So this error would be about 5% between the two. And now here at 20 degrees. At 20 degrees, that's going to be pi over 9. Okay, I believe. Yeah, it's pi over 9. Okay, pi over 9 is 0.349 radians. Sine of theta is 0.342. Now we're getting very interesting. Okay, this is off by 7 thousandths over 0.342. Okay, now we're talking about an error of only 2%. We get down to 10 degrees. Okay, at 10 degrees, now I'm saying that that's pi over 18, which is 0.1745. So the sine of that is 0.1736. That's 1% error. Oh, excuse me, 0.5% error. Okay, I'm off by only 9 parts in 10,000. What's it? 9 parts in 1745. So that's a 0.5% error. Finally, at 5 degrees. So now 5 degrees, that's going to be pi over 36, I guess it is, 0.08727. Yeah. Sine of 5 degrees is 0.08716. This is 0.1% error. The point of all this is that, especially less than 10 degrees, really, for our purposes, we can even do 20 degrees. Okay? But definitely inside 10 degrees, you have a very small amount of error. To a very good approximation, the sine of theta will equal approximately theta in radians. This is called the small angle approximation. Those of you in VC Calc will definitely be, will prove that, okay? We don't have to prove it, we're just using a functionally, okay, a functional proof of it. It has to do with what's called a Taylor series or a Maclaurin series. And we get to a very good approximation. Now, we can even make it better, but for our purposes, that's good enough. Okay? So now, let's take a look at a couple of examples where we're going to definitely take advantage of sine of theta equaling approximately theta. And it's theta in radians. So conceptually you might say, okay, I'm going to use 10 degrees, but you have to make sure that you convert that to radians. So now, let's just say I have a pendulum bob. Mass M, length L. Now, free body diagram of that pendulum bob here. Okay, I've got mg pointed down. Okay, this is going to be at an angle theta, which I want to keep ideally less than 10 degrees, but the up to 20 degrees, really 2% error for kind of activities that we do. If we get 2%, we're very happy. I also have a tension that goes this way. Okay. Now, here's the thing. Okay. This angle would also be theta. Put T over here. Okay, so this would also be theta. So that when I calculate the torque, I have it there. So now if I do the torque, sum of all torques equal I times alpha. Well, this tension goes right through our rotation axis. So the tension here doesn't provide any torque. The only thing providing torque to this is gravity, mg. So now the torque that this provides about this point, that mg going at the force is mg, okay, it's trying to make it rotate clockwise, so it's a negative force, a negative torque, at distance L away, at an angle theta, sine theta. No other forces act on it, okay? T is tension, okay, we could put that in there, but we'd wind up with 180 degrees, so sine of 180 would be 0. This has to equal I times alpha. Well, let's make use of that small angle approximation then. Okay, I have here alpha is equal to negative mgl over I times the sine of theta. This doesn't help me out a whole lot. But when I say sine of theta is equal to approximately theta, now I can say for a pendulum, now this is general pendulum mostly. If I make that quick simplification over I is equal to times sine of theta, or I just call it theta. This is the angular acceleration. This is the angle. I've got a negative, I've got a constant of proportionality. Okay. This is that differential equation that shows us, and usually we write it like this, just showing it as a differential equation. Okay, this is what shows us that we have simple harmonic motion. Now, this also tells us that omega squared is equal to mgl over I. Okay. So my angular frequency here would be mgl over I. Square root. If I want the frequency, Now, let's just say I want the frequency of this. Okay, so omega is 2 pi times the frequency. This is one thing that's useful. So 2 pi times the frequency is equal to root mgl over I. So my frequency is equal to 1 over 2 pi root mgl over I. Or the period would equal, which is 1 over the frequency, it's 2 pi square root of I over mgl. Okay. All right. So now this just kind of sets up some things with this. We're going to make a couple of simplifications to this. Okay, for a simple pendulum. Okay, for a simple pendulum, let me just move that over kind of. We're going to assume all the mass is at a point. Okay, in other words, the size of the mass is much smaller than the length of the string. So I don't have to worry about factoring in that this is a sphere or cylinder or some oddly shaped thing. Okay, I just call it some sort of concentrated mass at this location. Okay, that's going to make I equal to ml squared. Okay, remember a mass rotating about a point. Moment of inertia is ml squared. Or mr squared, depending on how we set it up. So now the period here, and this is the period of a pendulum, a simple pendulum, 2 pi I, which is ml squared, over mgl. Now would you look at that? First of all, one of the L's cancels out, but the m's also cancel out. So for a pendulum, the period of the pendulum does not depend on the mass. So the period is equal to 2 pi root L over G for a simple pendulum. And you can solve for frequency and angular frequency and everything else like that. But the period of a simple pendulum is 2 pi root L over G. For a physical pendulum, okay, let's just say for a physical pendulum, we could take a meter stick, and we're going to take a look at the period of a meter stick. This is not a simple pendulum. Okay, the mass is here. Okay, it's got length that goes all the way down. It's not concentrated at one point. We can't use the center of mass. Okay, because remember the stuff up here rotates differently than the stuff down here. So let's take a look at how that works. Okay, same setup as before. I'm going to do it for a meter stick. Okay, I'm going to say that the mass is right, the center of mass is right there. Okay, it's going to force mg going down. This is at a distance L over 2. Okay, it's also got the force of the pin right here. That does not provide any torque because it's at the rotation point. Okay, so there's only one force that's providing any torque. The torque that this gives is, okay, if I do some wall torques, I'm going to do it from first principles, just so we can kind of get familiar with it. The torque that this applies, this is angle theta, this will be mg, it's going to be L over 2 times sine of theta is equal to I Now, the moment of inertia for this rod about its end, well, I'll just call it I for right now, I alpha. I for a rod at end. Okay? If you remember back, you can check. This is going to be 1/3 ml squared. Okay? So now, I've got mg L over 2 sine theta is equal to 1/3 ml squared alpha. Masses drop. Yay. L, what are the L's drops? That. So now, let me get alpha by itself over here. 1/3 L over 2, so I'll multiply both sides by 3 over L. So I have 3G multiply by 3 over L over 2L sine theta is equal to alpha. I think I got the algebra right there. 3G sine theta 2L is alpha. Okay, this is making it rotate negatively. This is a negative torque. So I've got negative here, negative there, negative here. So now, I'm going to flip sides and make the small angle approximation. Negative 3G over 2L theta. This is, again, simple harmonic motion. Okay. So now omega is equal to 3G over 2L. Omega squared, that is. Okay. Omega is equal to 2 pi over t. So 2 pi over period is equal to square root of 3G over 2L. The period is equal to 2 pi square root, well, 2/3 what we had before, 2L over 3G. Here's what I want you to do. You have a meter stick in your house. Okay? See how much time it takes to go 10 full swings. Okay? Just take this, okay, mass doesn't matter. 1, 2, 3. Okay? You might have to give it a little bit of a push. It's not going to be exact because we don't have anything that you can clip it onto here. We're going to do a quick experiment in class to see how well this matches up with reality. But just for yourself, see how well this works. See how much time it takes to do like 5 full cycles. You know that the length is 1 meter, G is 9.8, and you can do a calculation. Okay? But do that for yourself. All right, I'm going to stop there. Remind me that we have to talk about the physical pendulum when we get to class. Okay? Physical pendulum. Anyway, have a good day. And remember, we have a test on Wednesday.